Esse me avisa a hora que eu tiver que começar, né?
Tá. So, morning everyone. I'm Professor Julio, and I'm here as chair of Professor Marcelo Becker. He's going to present some of his works towards agriculture using robotics. I hope it will be a very nice presentation and there will be lots of interaction from you, the audience. But I'll just pass the word to Professor Becker. Please, Professor, you can start when you want.
Okay, good morning, everyone. Thank you, Julio, for the introduction. I would like to say that I can't tell you what a privilege and a pleasure is to give this talk today. After the two previous talks, they were really great. I hope that you also enjoy my talk. Today, I'm going to talk about autonomous robots in agriculture to show you some of the research that we are doing last years at USP in São Carlos, and to give you an overview about what's next, what we still need to do, the partnerships and so on. Okay, so I'm from University of São Paulo. In the beginning of this presentation, you showed just a little bit of our group. So you can know that we are not in São Paulo City, we are in São Carlos. Okay, so we are in the countryside of São Paulo State, in São Carlos City. We are like the redneckers. Okay, São Carlos is a very nice city, and we have around 30,000 students in the city. And the most important thing is that we have a very nice ecosystem for innovation. So this is great for us at USP and Federal University of São Carlos and so on. We like these transversal projects, and we work, my group especially, we work very close to the Optics and Photonics Institute, CEPOF, from the Physics Institute. Okay, so we are technology pole, and many projects relate to innovation, lots of startups and so on. I just want to show you that as São Carlos is a smaller city when compared to Campinas or São Paulo, things are very close to, and we can work together easily with like Embrapa and the Federal University of São Carlos. Okay, here just a Zoom. It's nice because if I want to have a coffee with my colleagues at CEPOF, it's like a 5 minutes walk. To Embrapa is like 10 minutes walk, and we can share ideas. And you know, coffee, it's very nice to have good ideas. Okay, so CEPOF is very important for us. It was a great opportunity for our mechatronics group to work together with CEPOF. Professor Vanderlei Baiato is the chef of this group. And we work in this area, innovation area. So we are trying to take to the fields or to get this, instrumentation to the fields and to apply them. Okay, good. So those are the guys that work together for me: Professor Adriano, Professor Daniel, Glauco, Thiago, and we have these 4 collaborators from Federal University of São Carlos: André, Kevin, Rafael, and Roberto. Our logos, the areas that we work on robotics, IoT, AR, VR, blockchain, 3D printing, and artificial intelligence. That's me, if you want to get in touch with me later. And finally, what we do. In my group, we really do field robotics, and that's not easy. It's very hard to leave the lab, to go to the farms, or to go to run some experiments in outdoor environment. Most of you know that it's hard, but it's so pleasure to have the students working together and to get good results. And why do we do research focused on agriculture? So maybe the most important point is the population growth. So today we have around 8 billion people living on Earth. But in 2050, this number will be very close to 10 billion people. And, we need to feed everyone. According to United Nations, we need to increase a lot our food production next years to feed all these people. And to increase the production means not to increase the production area. We need to increase productivity. And we need to take into account climate change and environmental issues as well. And in this scenario, robotics comes as a very important player, okay? 5 years ago, we had around 800 million people that couldn't get enough nutrients to have a healthy life. And this must change. Otherwise, we are going to have big problems in a few years. And not only think about that, but thinking about business. Agribusiness is a very big, very important thing in Brazil. So you can see here the numbers. I'm not going to go in details, but it's important to highlight that although Brazil produces lots of crops, grains, and other things, we need to import lots of goods to increase our productivity. So somehow we find ways to improve and to optimize the use of these goods. It would be great. Here I have some news in English. So just to give you an example of what we need to import, fertilizers. This was last year, 2019, in Santos port. It was the hugest cargo that came in one ship. It was like 72,000 tons of ammonium sulfate. We don't produce this here, so we need to import all these goods. And just to highlight, ammonium sulfate is different from ammonium nitrate that explode in Lebanon. It's different things, okay? And every year, only in Santos port, we import something around 7 million tons of fertilizers. So it's really a big, big issue for us. Business also, we have in this region of the countryside of São Paulo State, Agri Show is the biggest demonstration and festival in this area in the country. Like in 2019, we had 2.9 billion reais in business, selling machines and other things. This year, unfortunately, we didn't have it. 2020, we didn't have Agri Show. Okay, so I'm going to show you some difficulties that we can find in this area in agriculture robotics. First of all, we would like to have something like this. My scenario, I have some robots that are docked. I can provide energy for them using solar energy. I can send all the data to the cloud, process the data, and have a feedback for the robots. I can connect everything. So this is what we would like to have. It will gonna take some time. Probably in a few years, this is gonna be a reality if you have some, experimental farms where we are developing research. This is feasible to do. Here in São Carlos, we have an experimental farm from Embrapa, instrumentation, and like in Exalc, there are other experimental farms too. We can provide this infrastructure in these research farms, but it's not what's going to happen in the fields. If you go to Mato Grosso, Goiás, or other huge states in Brazil that we are producing lots of crops, it's not like this. So we need to increase and provide good infrastructure to have this scenario. Yeah, and taking into account this article from Center of Digital Agriculture in Illinois University, we have here the levels of autonomy for AG robots. So from level 0 to level 5. Today, we start in level 0 and we are increasing the level. If you see, level 0 is full manual teleoperation of the robots. So there's a student or researcher there that's operating everything. Level 1, I have the robot within line of sight. So I can see what's happening, and maybe after 5 minutes, I need to do something because the algorithms in the robot are not that good. And then I'm improving little by little the algorithm so I can have less interventions. I have a larger autonomy for the robot so it can start to do things by itself. Okay, So as an example here, level 3, human decides it's too wet to go out because it's raining or something is happening. Level 4, robots decide it's too wet to parts of the field, to go to parts of the field based on in-field sensors, so it can take decisions by itself. And level 5, robots are expecting that it to be too wet to go out, but they make sure the job will get done nonetheless. So it will figure out a way to take decisions and get the job done. But in this area, we have some difficulties. Let's say some positive obstacles. So you can have this power, transmission power towers. You can have another vehicle in the middle of the way. You can have buildings there that were not mapped. You can, because of rain, you can have mud, erosion, and things like this that you need to adapt your path planner and so on. So you can't count only on GNSS data. You need to have a good perception system to look around, check what is happening, and take decisions. And we can also have some people walking around, other machines, animals, and uneven terrain. That's sometimes very difficult to overcome. Good. And in addition to this, let's say that taken like an example, adverse conditions, the sunlight brightness change during the day. So when sun is rising or sun is setting in the middle of the day because of the clouds, just lightning conditions, brightness conditions change a lot. You have the weather conditions and so on. You can have fog. And if you want to have a robot that can work 24/7 autonomously, you need to take this into account. Good. Another problem, I would say challenge, is that every kind of crop has its characteristics. So they differ, not only size, shape, but also on the way that people are planting them. Okay, so you need to take this into account too. And many times you need to design a robot that will go to the field, check what is happening when this crop is small, and as it grows, you need another robot because it can't go there anymore. Okay, so there is no Swiss knife that can solve all your problems. I like to say this: robot for agriculture, they can't be a Swiss knife, otherwise they will be way too expensive. Taking as an example, soybean. In Brazil, the row spacing varies a lot from 0.4 meters to 0.5 meters. So depending on the region of the country, they plant them in a different distance. Okay, and you have this growth stage. So let's plan to build a robot taking into account those requirements. 0.45 meters, a crop distance of 0.05 meters, and just for the beginning of the growth stage of soybean. So it'd be a robot. Complete different of the one here highlighted in this red rectangle, because in this stage, the soybean starts to grow and all the leaves get together and have like a tunnel in the middle of them. So a robot that would go in the beginning, maybe it can't go when it's bigger. Okay, good. Another point, as I told you before, we can't trust only on GNSS data. Okay, the environment is changing, and problems can happen. Let's say if you have a military maneuver, the owner of the GNSS system can add some errors in the data that you're getting. We can be in an area where we have a magnetic anomaly, like we are here in Brazil. You can see in the bottom of the slide, this figure, the South Atlantic magnetic anomaly. So it doesn't work that well. We can be in a situation like a cannon, it can be a urban or natural one, or you can be under the crops and you don't have GIS data good enough to navigate based on this data. Okay. So to have an autonomous AG robot, we need to think that we are dealing with field robots, drones and ground robots. We need to have lots of effort to develop learning systems, machine learning, management processing, and lots of control theory, adaptive control, reinforcement learning, and so on. You can see that we are full of challenges, and we should not forget the costs associated to those robots. And I see not only challenges, but also opportunities. So it's really necessary to think about teamwork. It's not only a mechanical engineer or electrical engineer, computer science guy. It's teamwork. We need everybody working together to face these difficulties. So some companies are working on this. I'm not here trying to make advertisement of any company. I try to get some big companies that are developing some such systems, like the C8 case. In 2017, they showed the world this, I think there was the first tractor, autonomous tractor. You see that there's no place for a driver. Okay, up to now, it's not, as far as I know, it's not on the market, but it was 3 years ago. And John Deere did the same last year in Agri in Hanover. So they launched this tractor for farm automation. Here you can see some more pictures. It's big tractor, very powerful one. And again, no seat for a driver. So it runs autonomously. Here you have lasers, IMUs, GNSS receivers, and so on. Okay. And John Deere also invests on drones. Okay, in the same festival, Agritechnica, they also launched this concept drone for farm automation. Okay, but Brazil is not behind. Jacto company is a great company here in the countryside of São Paulo state. Since 2011, they are doing research with this autonomous sprayer. Sprayers are very big, are a big issue because you know the person that is driving the sprayer can get contaminated by the pesticides. So it's important to do it in a safe way. And Jacto is investing for the last 9 years doing research in this area. The last year they have this second version, and as far as I know, they are launching this year this sprayer for the market. Research labs, many research labs around the world. I just tried to highlight some here, but there are many more. And I'm gonna show you some research that my colleagues in Illinois and we at USP, we are doing. Part of the things that I'm gonna present to you, we are doing together, part not that together, okay? So my partner there is Professor Girish. He's working in this agricultural and biological engineering department in Illinois, Urbana-Champaign. And in my case, I'm working on this area since 2009. But my department started to develop research this area a little bit before. 2005, Professor Arthur Porto started with this RAM project. So it was an electrical robot that could go to the farm. It was a partnership with Embrapa Instrumentation in São Carlos. They could embed some sensors and check the things about the plants, okay? So 2009, I was invited to work with his lab and Jacto in this AgriBoat project. I'm gonna show it in a few minutes. And since then, I decided to look more careful. And you know, I saw a great potential and lots of challenges, opportunities in this area. So my group started to develop, in the beginning, little robots, and then we are increasing little by little and making more sophisticated versions of the robots. So we had this Miran, R2A, Elvis, and in 2017, we started this collaboration with people from Illinois, Urbana-Champaign. So they donate for us this first version of Terra Sentia. And since then, we are developing more and more prototypes in this area. This year, although we were in the middle of the pandemic, our colleagues in the United States sent to us a new version of the Health Center, the 2020 version. And the last one is Agri Sphero. That's the project that one master student of the group just present. I'm going to show you a little bit about it in the end of the talk. Good. So basically, what my colleagues in the United States and we are doing things very similar. We have the same beliefs. We want to have aerial robots and ground robots working together in a way that we can, do inspection and maybe interventions in the field if necessary, in a way that the farmer can control what's happening, seeing the results using a tablet or a smartphone. And the robots must be autonomous. We can't ask the farmer to operate the robots. It should be something like plug and play and not plug and pray. Okay, so 2014, as soon as we ran the first demo of the robot with a lead sensor with Embrapa people, the newspaper here in São Paulo State, Estadão, they made this nice picture showing the idea that we are working on. Okay, so my job is not to develop the instrumentation, but to work on the ground robot and the air robot. It's funny because they used in this illustration fixed wing air robot, but we don't work in my group with this kind of robot. We use quadrotors and exarotors. So the first project, AgriBolt project, as I told you before, this was a cooperation between my lab and NEPAS, Núcleo de Ensino e Pesquisa em Automação e Simulação, and Jacto Company. So basically, Jacto Company, they built this prototype, and we, in my group, we worked on the controllers and the steering system and navigation controllers. Okay, so it was a big challenge for us because I don't know for you, my colleagues, but here in São Paulo, we don't have many guys that work very well on hydraulic systems, controlling hydraulic systems. So it was new for us in my group, and we could learn lots of things about this. I know that there's a very strong group in Florianópolis, in Universidade Federal de Santa Catarina, but here at USP in São Carlos, it was something very challenging for us. Thanks God, our students could do it. Okay, and after that came Miran project. So it was just a demonstration robot. The idea was to take the leaps. I'm going to show you what leaps is in a few seconds, to the fields and prove that it was possible to have a portable lead sensor that we could get some results and then they could work with this. Okay, so in 3 months, they made this box, let's call like this. It was very low cost just to take it to make a demo. Okay, so here you can see the Miran with a quadrotor. So we made the top part of the robot flat so we can use it to land and to take off the drones. It was a big success for them. The idea was just to go to the experimental farm of Embrapa and show it running some experiments in the middle of a cornfield. And LIPS is this. NASA has the same sensor. I think you could see the flash. The same sensor, you can analyze the soil without taking the samples to a lab. So you can do everything in local, in the fields, okay? So it's fast, maybe it's not that precise. To make it more precise, it's necessary to have before lots of calibrations. And you need lots of sample soils of everywhere in Brazil, and then you can compare the results and make the algorithm very good. So this is Embrapa's job, not my job, okay? And it was very nice project. Oh, sorry. Here you can see what they get. So you have that flash. There you have plasma. So you have a way to get that image, take the image to spectrometers, and then you can analyze that the quantity, the intensity of the light, and the length of the wave, and say, okay, let's say number 1 is carbon, number 2 is nitrogen, and so on. Okay, that's what they do. But this is Embrapa's job. So after that, we could get financial support to make something more, that could look more like a robot, not like a box. And I got some students that start to develop new designs for passive suspensions. So what they do, they went to check what we could find in the literature. So some rovers that we could find from NASA and the European agency. They made the models, they simulate everything, they could run some experiments, nice images, they could check the limits, okay? And it's nice. It's nice to have a rover with 6 wheels. In the end of this research, I was a little bit disappointed because I was expecting to have a rover with 6 wheels in my group, but they gave me just 4 wheels. But they could prove me why, okay? They could run some experiments and show that for our application, it could be a simpler solution, cheaper solution. So we start with this initial idea and evolved using very low-cost models. This, this Bosch models for the windshield wiper. We could control them and so on, and it evolved a little bit up to the moment that we had this. So the first prototype draft. From the initial idea for the first prototype draft, we could make it. It was John Faber's PhD dissertation. And then he made the prototype. He ran some simulations before to prove that it was stable enough for what we want. And then the first prototype. As I told you before, it was a very low cost. So the performance wasn't very good, but we could see what's happening and check what we would need to do to improve that very first prototype. So this was in 2016, 4 years ago. Again, we could prove that we could do a good job. So we get more financial support, a new budget, and then we evolved from R2A to Miran 2. Okay, so it was like a medium-term project. The idea, it's a long-term idea, what Embrapa would like, and this will depend a lot on the developments in the leaf sensor, is to optimize the use of agricultural inputs. It means that we need to quantify macro and micronutrients in the soil. And the idea is, as I told you, to avoid sample handling. I don't need to take it to the labs. Makes life easier. And doing so in the field, in local, I can get geo-referenced data. So I can have like a 2D map of the environment and check which element I need to put where to have a better soil for the crops, okay? And another thing that they would like to do is to have this early detection of disease vectors and agents. But this is a little bit tricky to run experiments because, we can't let the diseases and these vectors, we can't spread them in the field, otherwise we are going to have a big problem. And the idea is to, in the future, to have a kind of, greenhouse where we can run this with all the things necessary to keep safety, okay? So the rover, the idea is that we would have a vehicle for tests and proof of concept. It must be off-road and autonomous. We need to develop all the controllers, navigation systems, etc. And we need to define the set of embedded sensors, not only for monitoring the crops, but also to navigate the robot, okay? To do so, we divide the project into two sub-projects. A group of the students was working on the design of this new rover, and another group in this Elvis project that would develop the first controllers. So for design of the robot, we used well-known tools like SolidWorks, MATLAB, Simulink, Inkscape, and all the model of the robot. We run some simulations, and this is nice because the students in the beginning, they want to run the entire robot. I told them, no, just one wheel first, steer the wheel, drive the wheel, and then you think about the whole robot. Otherwise, you're going to have so many problems, and you never find where the error is. And we went to Adams later, so we need to model this 5-bar mechanism body, the steering motors, the driving motors, and we need to decrease the complexity of the model to make these simulations using Adams. Here, just an overview of the model. And then we could have some things like this, where you can see the very stable behavior of the platform. I always want to have this because I was thinking about the drones landing and taking off on the top of the robot. So we could have this collaboration between aerial and ground robots. Okay. After that, after the simulations, we need to decide the components. Okay. So we went for Apple's and Maxon motors. Apple's drivers and Maxon motors. We used the Advantech computer and all these connections and make it work. Okay, so in the end, they could estimate that we would have a kind of electrical autonomy of 63 minutes if the robot was going uphill in a 32 degrees slope. It's good, because usually here in São Paulo state, the area is very flat. We don't have such a slope. Okay, I'm going to skip this because this is the mechanical parts. And okay, so in July 2018, we have this new version of Miranchu, the new rover. Here, at this moment, the LIB sensor is not embedded yet. They were developing the LIBs at Embrapa and at the Physics Institute, but we could start to run some experiments. The size of the robot is this, 1.10 meters by 1.10 meters, 1.20 height. And this is because we decided 2 years before that we would work with soybeans. So taking into account, remember that distance between the plants, we developed this robot. Okay, so here you can see all the pictures of the robot in the workshop when we were assembling everything. And this is the LIB sensor that we would embed the system. And this is something that we really need to work on. So to get a better view, we couldn't rely only on optical fibers because the flash of the laser was very close to the ground. So it's like 65, 70 centimeters away from the sensor, and they need to use a telescope to get a better image. So people in the optics and photonics group, they are working on finding a way to eliminate this telescope to make the system smaller, more compact and lighter. Okay, because in the beginning we were thinking about some like a shoebox of 30 kilograms, and then it became huge, much bigger than we expect, and like 25, 30 kilograms more, heavier than we expect. Okay, so some pictures here for you. And those are the guys that were working the robot. Andrés Baquero, that was the leader of the project, the mechanical, electrical, electronic part, and Manuel Larenas that was working on the optics. Okay, so here you can, I hope you can hear the sound. This is the sound of the LIBs. producing the plasma. So that's what's happening. We were running some experiments in the lab here, so we could get this kind of curves. So the spectrum and the wavelength, okay? So we did all this before going to the fields. And that's just a plate that was turning to get the signal. Good. And because of the LIB sensor was way too heavier than we expected, we need to change a little bit the suspension. In the beginning, we didn't have any springs, and we need to change the position of the center of gravity of the robot, and this was very painful for the project. So we need to add some springs to have a better behavior of the robot in the fields. Okay, some more pictures. Here the robot ready to go for the experiments. So you can see I have 4 driving motors and 4 steering motors. So it's very easy to maneuver the robot even in small spaces. And here the robot in Embrapa Farm in São Carlos City. So we can see you can see the behavior of the robot. Okay. So that what I told you, that during the day the brightness changes. You can see when the sun is clouded by clouds, change a lot. Here is a typical environment that the robot would face. And this, you can see the problem. Here you can see the problem that we face changing the position of the center of gravity. The first time my students showed me this video, I was like, oh, but thanks to the springs and the passive suspension, it worked. Just after this stabilizes and we can continue. Okay, so in January 2019, we start to run some experiments. You know, to run experiments in the farm is not that easy. You need to everything in advance. You need to plant the crops, and doing so, we still face some adverse conditions. Like we didn't expect that some hares would go there in the plants. So it was a big surprise for us. We need to, you know, to build a fence, trying to protect that area and avoid that the animals, the hares, and would go there and eat everything. Okay. Okay, so you can see here the robot working just when the plants emerged. They're very little, and the robot passes. So we can add at this moment we were running experiments only with the navigation controllers and things like this. But later on, you can add the sensors and get some results for Embrapa people. So here the laser data. We're constructing the area around the robot, the camera. And in the beginning, that's pretty easy to navigate there, because even in the presence of wind, it doesn't bore you that much. But when the crops grow, you know, in São Carlos, we have lots of wind, so it becomes more and more difficult to navigate there with the presence of the wind. So we decided to create like these virtual walls that change the distance between them as the wind blows. So let's see here. So you see that the walls are changing a little bit the position. You have the left LiDAR, the right LiDAR. So I start to reconstruct everything to estimate where the plants are, to filter the leaves that are in the middle of the way, so I can navigate there without damaging the crops. This is something very important because Embrapa wants a robot to run experiments 24/7, and we should not damage the crops that they are growing. Otherwise, their experiments would be in trouble. Okay, after that, we were ready to go for Ciagro. That was Embrapa asked us to make a new demo, the second Ciagro. The first robot that we made, the first version of Miran, was the first Ciagro. This was for the next Ciagros. It took place in December last year, from 3 to 5 December. And the news again, so we could make this demo. Global TV was there taking things, and we could show nice results. Okay, in parallel of the development of Miran robot, we used Elvis to run some experiments for the navigation before Miran was ready. We couldn't wait to have the entire platform assembled to start to run some experiments. So we decided to use this small version, and it evolved along the years. So it was, in the beginning, it was like this. We went to the lab. We didn't have a farm, so we used these pipes to create, a farm-like environment inside the lab. It's easier to, to change the algorithms inside the lab than to go every time to go to the farm and see that there's a problem, and then, oh, I don't have energy, I don't have water, I mean fresh water, I don't have I have the sunlight on my face, and it's easier to start doing the research like this. So in the beginning, we plant corn, corn trees on these vases, and we could change the shape of the rows, the distance between them. The laser sensor, we add a wood block on the bottom of the laser sensor, so the laser would detect only the crops, not the vase. So here we could develop all these algorithms to enter the row, exit of the row, keep in the middle of the row. So it was nice for, the first algorithms. It was really nice. And we also used this, we developed these mechanical parts here to try to decrease the price of having a 3D laser sensor. We had some in our car, like a Velodyne, but we didn't want to use a Velodyne, that robot. So we got these Hokuyu lasers, and we were turning the laser in this way so I could produce a TD cloud of the environment around the robot. So it was like this. It's the same robot that we were using before. We just made some changes. So we had the front LiDAR and this LiDAR on the top assembled in this pole. So we could have two IMU sensors, and we did all those transformation coordinates. We went to Embrapa farm, and there we ran some experiments, and it was nice to develop the filters that could take away the leaves, because when the corn is growing, some of the leaves fall on the way, so you need to filter those and to see the area that you have that in front of you that you can navigate without damaging the robots, the crops. Good. Now, things that we did in partnership with Illinois people. Illinois people are working very much in this phenotyping, for lesson 9. They use corn as a good example of what they are doing. For the last 9,000 years, humankind are selecting the best seeds to have the best corn. Okay, so thinking about the population growth, they really saw that we need to accelerate this evolution of the corn and to have best seeds to feed humankind. Okay, so you have the genomics, you have the environment, have the phenotype. That's what they are working on. So they have huge areas. This is like a part of the experimental farm they have in Illinois, very close to the university in Urbana-Champaign. And you can see the guy here. So all these areas, in all these areas, you have different seeds of corn planted and other crops too. And they need to check one by one the best ones that they are gonna produce the best seeds for the farmers. So it's really challenging. Before they were using students, they were hiring students and people that would go there with all the equipments and to measure, to take photos, to check the condition, if the crop was growing well and so on, everything by hand. So you see that's too much work. Because of that, they verified that the lack of automation was a bottleneck. So they really need to do something to help them. You see things that they need to do, and they check that grant is not that good. They're great infrastructure. I saw it in Zurich. They use some kinds of grantees. Drones, if they think they are fixed wing drones, they fly too high. If you are planning to use quadrotors, they fly low, but it shakes a lot the crops, so you have a blue image that's not that good. And when it comes to robots, you have the autonomy problem. So they decide to invest on these robots. Okay. And another problem is that the scales are vast, and data is noisy, unlabeled, so someone needs to do it. And the environment is really challenging. If here you can see Terra Sentia, the right side of the slide, you can see Terra Sentia moving in the middle of corn field, so it's not that easy. Okay, and the idea is because you need to move under canopy, you can't trust GNSS data. You don't have it there. Okay, so here things that you can do. We are working together with them, so we can do it autonomously. This version of the robot is compact, and you can teach it to do many things, like here using image and to count the plants that are growing well. Okay, let me go ahead. So in the beginning, I sent a student there. It was Vitor Akihiro Iguchi, one of my best students I ever had. He started to work with the guys in Illinois, developing this LiDAR-based autonomy under the canopy, and it was great. We got great results. They checked different speeds, the behavior of the robot at different speeds, so we could evaluate this in the performance of the robot. We could see that really we can trust the GNSS data, so it's important to have this LiDAR. And now they are combining LiDAR and image too, so with cameras. In addition to this, sometimes they need to have a camera checking the crops up there where they are growing, where the seeds are. And to do it, so they decide to have this version of the Terra Sentia with this pole where the camera would be on the top. So you can see that's not easy. When it comes to simulation, it's pretty nice. Everything's flat and perfect. But when you have the robot moving on the field, you see that the terrain is not even. So sometimes it's hard. And because of that, we start developing this mechanism so we can have a control system and to increase the behavior to keep the camera in a better position to get the image. So here you can see the sensor's angle and the platform angle, so we could compensate that with that movement of the pole and keep it better. Okay. When it comes to maneuvering from one row to other row, depending on the crops, you can use GNSS without any problem. Here you can see Terra Sentia navigating from one row to the other row, so it's GNSS based movement, so it's not a big problem. It goes smoothly, and then to the next one. It's important to say that in this case, this robot has just 4 motors, so you don't steer the wheels. That's why it needs to take a long way, a big circle to go into the next row. Okay. And this is the situation that they're facing. You can see that the leaves are in the middle of the way, and you need to filter them. Another thing that they are doing is, I already showed this before, not only to count, but to measure the stand when the crop is growing. So they got really good results, and in some cases, much faster than a person would do, for sure. So here, the counting plants, as soon as they emerge, you see the average error is just around 5%, so it's great. You don't need a person to do that. You don't need lots of students to do that. And here to measure the size of the crop, you can make this 3D map, 3D view, passing through that tunnel. Let's call like this. And moving at 1 mile per hour, they could do this 30 times faster than a person would do. Okay, so it's really a great improvement for them. They use also other crops like tobacco and others. Okay, this is STEM with estimation, comparing estimation done by the LiDAR and the camera. And then they can cover everything and go. Okay, so it's very close, the data that they got. With detection, what is not corn, so they can map this, and in the future they can spray something there to kill it, or to have a kind of arm and, you know, to take it away. And also we like to work in these simulators. It's nice because you can have hardware in the loop simulation. You can prepare everything. Everything is running on ROS, so it's pretty easy to plug and play after hours. And it's nice because you can also think about having a fleet of those robots working together and optimizing the time necessary to check all that plantation field. You can plan everything. Okay, so in 2017, my colleagues in Illinois sent us this first model of the Essentia. The second one, my students work with them in the US, and now we have the third one that just arrived 2 months ago in Brazil. So it's a pity that now we can't run some experiments in Embrapa Farm because of the lockdown, but my students is with the robot in his hometown, and you know, he has now tons of data, and he's working on this data, trying to finish his PhD. Basically, the robot has the sensors, INU, a LiDAR, cameras in the front and on the sides. You can adjust the camera position. So if you want to see something that's close to the ground, like the roots growing and to count the plants, or if you want to see something that's upper position, you can change this. You have these wheel encoders and GNSS antenna that you can use to navigate. This is a movie that shows the robot working there, a short movie.
Professor, we can't hear the video. I don't know.
Oh, sorry. Oh, my apologize. I apologize for that. Basically, she was telling you what I told you before, that they are using a robot to improve the production of food. That's the best way they could figure out to get those data without the need of lots of people working in very hard conditions, you know, on the sunlight. It's very, very hard for them. And based on the results now, they can improve the quality of the seeds, and the main companies like this, and they are starting to sell this robot in the US for other companies. Okay, sorry for the voice, it didn't appear. Okay, so I'm going to the end of the presentation now. We are going to talk about our last project, Agri Sphero. So it's from Guilherme Marques Martins. He just presented his master degree dissertation a few days ago. The inspiration came from this robot, the Rotundus brown robot that was made, designed some years ago for surveillance. And the idea is that sometimes the crops grow and the leaves, they get together. You have like a tunnel close to the ground, but you can't inspect that area if you're not allowed to go inside. And with robots with wheels, that's too hard to do, because maybe you need a very small robot. So we start to think to have like a spherical robot that could go there and have something like this with these cameras or illumination system that I could see what's happening from the bottom. Okay, so based on that idea, Guilherme started to develop a new proposal, a new design. So he got these two different designs, and he built the two ones, and the last one is our actual prototype. Okay, so here you can see what's happening. It's, for the moment, it's big. It's like 30 centimeters. The diameter of the robot is like 30 centimeters, but it was the first prototype. Now we want to downscale it and work with the instrumentation that we can add to the robot and then run some experiments. So this is really the first stage of the research, but it was really great. Guilherme did a great job, and now he is applying for a patent for this, the mechanism, because he developed a new mechanism to do this. Okay. And we also work with these aerial robots, the quadcopters. My group, not only in simulation, but we also have some helicopters, and we develop new ones. We have commercial ones, and we develop new ones because we noticed some years ago that the biggest problem with these robots is that they are very nice to fly indoors, but when you go outdoors, the presence of wind, as I told you, São Carlos, we have a very strong wind. So when we go outside to run some experiments, like the battery gets empty 15 minutes after the beginning of the test. So it's too low autonomy. And based on that, we decide to try to develop new designs that we could improve this time of the experiment. And thanks to the collaboration we have with Aeronautics Department, we can not only, it's like really an engineering project. We design, we model it, we test in the flying, the wind tunnel, and then we go for the flight tests. So it's nice because the wind tunnel tests, they really change the design then in the end. Okay, so thanks to this partnership with the Aeronautics Department, we can do many things. And this is another research area that we have in the group, but I'm not going to tell that much in this presentation. Okay, so I'm going to the end of the presentation. Some conclusions. Where we are, our group. We start here for sure, level 0. The first prototypes in the beginning, in all the cases, we were teleoperating the robots. And then we are almost going to number 3, level 3. Okay, it's a period that the lockdown really stopped most of the things we were doing here in the lab. So it is going to take a year for us to be back in the race. Okay, but thanks to our partnership with our colleagues in the US, they are almost reaching level 3 too, and it's great job that we are doing together. Next steps. We want to work on the cooperation between rover and drone since the beginning, since 2014, when we had that first box, let's call it this, the Miran one. We had this dream of having a cooperation between both. Okay, so this is something that we are starting now. The cooperation with the rover and the Agri Sphero too. It's nice to have a robot that goes to the field and then leave these small robots that can enter some areas that the big one can't do, and then comes back and share the data. It's nice. We are working on this embedded perception system because things are not that cheap. Some sensors are very expensive, and we need to find the balance between getting the best data and something that's not that expensive. So it's always a matter of finding the balance, okay? And for sure, navigation is one of our priorities for us of the group. That's why we start to collaborate with the Americans and the students that did really a great job. Now I have two students of the group are already there working in the US with them, and one is still here finishing the PhD. I really hope that he stays here. It's Akihiro. Let's see. And for sure, deep learning and big data, because this is, you go there to work this not only LiDAR, but image to extract the features and everything from the image and mix them with the LiDAR. We will go for deep learning, and to get all those data, big data, it's nice, okay? So it's essential for us to have partnership with instrumentation and sensor companies to develop this inspection agricultural robots. And this is a big issue for us in Brazil. It was easy when I was in Switzerland or for my colleagues in the US, to push the suppliers and they can provide better sensors the way they need. So this is something that we have problems in Brazil. We need to import those, and we are not in touch with them to ask them to develop things that we need. An example of this I can show you here when it comes to autonomous cars. This is the Hyundai Nexus 2018. It's autonomous car, but you don't see the sensors. Everything is embedded in a way that they are small, they are cheaper. Some are mass production sensors, some are developed just for Hyundai, and you see the evolution between 2007 and 2018. 11 years passed, and look, you don't see the sensors. It's amazing. So we need to have the same thing in agricultural area. It means that these big players need to use some pressure on the suppliers. Okay. As I told you before, there's no Swiss knife for AG robots. Depending on the crop, you need to develop something different. Okay. In the case, let's say you need to detect a disease, but you need to understand if the disease can be detected close to the ground or up. So different applications, different robots, and it's really challenging, but lots of opportunities. So to develop this. It's a teamwork job, really teamwork. We need to work together, okay? And we need to have investment. I believe that the universities have a great job to be done, but we need to have this, the companies understand that we can work together, but they need to give us financial support. Otherwise, we are going to lose all our best guys for the companies and the universities abroad. Okay, some days ago, we had this the webinar. It's on the web. So it was a great opportunity to have some research from around the world. I was the last one here, but I didn't present anything. I was just the bad guy controlling the time and tell them, okay, it's time to stop. But it was really great. You can check on the web. Okay, it was nice to see their views about the future. Okay, and next week we are going to have another talk about this field. It will be next Monday, so it's for free. It's for Sematron. Sematron is Semana de Engenharia Mecatrônica from São Carlos, USP, and I think you are going to like it. We are going to have not only this professor from the US, Jewish, but also a guy from NASA and another one from Facebook, and it'd be great. We have open positions in the mechatronics group, okay, second semester, because the first semester selection process already finished. And we really like to share our toys. So we are open to work together with you. If you want to run some experiments, if we can run the experiments and send you the data, it would be a pleasure. We need to work together. As I told you before, it's a teamwork. We can't do everything together. I mean, alone. We can't do everything alone. We need to work together. So acknowledgements, I would like to really thank the organizing committee. It was a great privilege and pleasure to have the opportunity to show you what we are doing here. And I really would like to thank the IEEE South Brazil Robotics and Autonomy Society chapter. Although the names is South Brazil, São Paulo is together. Okay, we are together in this chapter. And USP, some of our partners. And if you need be in touch with me, here you have my mobile. I won't be in the office up to March, but you have the phone of the office here, my mobile phone, my email. It would be great to talk to you. Thank you very much. I'm sorry if I talk too much.
Thanks, Professor. Definitely a very, very interesting presentation, and also very well made, actually. Congratulations for the presentation itself. It was very well structured, and the animations and the focuses were very well placed. Do we have any questions from the audience? Please raise your hand if you have a question, and I will pass to you. And I saw a comment from YouTube. Some people congratulating you and your team for the work. No question from you for now, but definitely I have some questions, actually, lots of questions. But I will just start, and I think you mentioned it in the beginning, but I think we need to think more carefully, and I really don't know. It's actually a curiosity of mine. How is are we yet in the point where we can think about the investment versus the outcome from the point of view of the farmers? So are there farmers that invest in this kind of technology, and do they have some outcome? Do they say that, okay, it's nice, I will invest more money on it?
Okay, so this is an excellent question. Thank you for making it. I think we should divide this into two different kinds of farms. We have, three. We have small farmers, we have medium-sized farmers, and big farmers. So for the big ones, for sure, it's we can do it. The price is not that high. Okay, the challenges are high because, as I told you, different kinds of crops, you need to have different solutions, and you need to understand the mission. What's the mission? To detect a disease, to count the quantity of plants that are growing. We need to understand their needs. So I really like to work on this field, but thinking about the design process. So you give me the requirements, and then we think about the embedded sensors necessary, the instrumentation necessary, and the shape of the robot, how we can solve that problem. So this is one thing. For little farmers, solutions must be cheaper. We need to take into account if they have, people to work with them. This is becoming more and more difficult as the Brazilian economy is growing, and not only Brazil, but everywhere around the world. If the economy is growing, the population is moving from the countryside to the big cities. Few people will be in the countryside producing food. So we need to find a way that is cheaper. We can find a balance between the investment and the pros and cons, and to give them, to offer them, machines. Sometimes you can tell them that this is a robot, this is like a tractor, it's gonna help you to do your job and to increase the productivity. So today, for the big farmers, I think we already can offer good solutions. But for the small ones, it's tough. It's really tough at this moment. But I like to use as an example the mobile phone. When I finished my PhD, before I finished my PhD, I had the opportunity to go to Switzerland to work during some months. I think it was 8 or 9 months at ETH. And back at the time, I didn't work on vision because it was too expensive. The LiDARs were too expensive. And we didn't have enough processing power to have inside a robot and to process all those data. But today, the mobile phone, you have everything there. So some years ago, 8 years ago, a student of mine, he did his diploma work using a mobile phone, and he implemented that mobile phone 8 years ago. The Kalman filter, the extended Kalman filter, he used the camera, the IMU, everything. So the price of those sensors and the processors are decreasing a lot. So I see that in the near future, we will be able to offer the farmers better solutions for a reasonable price. Did I understand? Did I answer your question, Julio?
Yeah, in many directions. It's nice. Okay, I saw lots of research, and I have some friends that work specifically in Europe in this direction. Agriculture, focus robots, and maybe most of them they will speak about the same issues that you mentioned, specifically with the navigation on the ground. On the ground terrain, and also the all unpredicted things that could happen with light, occlusion, rain, humidity, crops, and many other issues that could appear. We have some comments on the Q&A about the costs involved, but I can't see any questions right now, just comments. You can read afterwards if you want. But I have another question, so we still have time. So we have 18 minutes until the next, the beginning of the next session, so we can just talk. And I have, actually, it's a question from yesterday when I was watching to Professor Van Gaal presentation, and he won't mention this direction, and I want to ask you, maybe because you are also working with autonomous robots, and when we say autonomous to people, they are just they won't trust the autonomous thing. Some months ago, I bought vacuum cleaner robots for my house because we have 2 dogs and we had to clean all the day. Mm-hmm. And my wife, she won't let the robot do the job alone. She'll just stay there and watch the robot to do the job. Still, it's doing autonomously, but she won't trust it. She won't trust him. Mm-hmm. And that's a question that goes in this direction. So are you or do you know any research that's working on the direction of semi-autonomous robots, maybe helpers that will increase the productivity, but won't do 100% of the job, or at least will do it with the supervision or active supervision of a human being? Thank you.
Yeah, I agree with you, Julio. Many times it becomes too expensive to make a robot that can do everything autonomously. So if I have a helper and I can trust and I can interact with the helper, it's great. And last years, thanks to Rethink Robotics, we start to have this relationship between robots and humans closer way, let's say like this. So you could, you don't need to stay outside of an area protected by fences and sensors trying to detect if someone is entering that area. So you could have a robot by your side, and if the robot hits you, it would change the controllers in a way that it wouldn't hurt you. So, okay, so you start to trust the robot. I don't know, probably you already know this, but many times when I have this very close relation between humans and robots, mainly when human is doing the maintenance procedure of the robot, something wrong can happen and the robot can kill the person, and the robot would feel nothing because it doesn't have a perception system to know that there's a person by my side. Okay, so this is changing. This is something that I try to show my students, that the word for them will be very different from the word that I knew when I graduate. Things are changing in a very fast way, and I see that the robots will be more and more close to us. So if you think about this balance between cost and benefits, maybe the best option would be to have a helper than to have a robot that does everything alone. Okay, I agree with you.
Okay, thanks. Elio has a question. Elio, I will read your question, but if you want to speak and comments with Professor Becker, just raise your hand and we will allow you to talk. So he's asking, what's the reason that are few manufacturers of the agriculture implements that use national technologies in their products? So he says that the government invests a lot in research and production, but there is a region. Is there a reason that that leads the manufacturers to use? I think it's international technology, not national.
Okay. Yeah. I see. Wow. Let's see if I understood the question. Many times the manufacturers are in a very, how do I say it, comfort situation. They don't need to invest that much because the customers don't express their needs. So they don't feel that the customers need something different. And if something new comes and shakes everything, and the manufacturers will observe that, oops, I need to change. I need to bring new features. I need to do something different because there's another company that is doing it. It happened some years ago with Rethink Robotics. So you had that big companies like KUKA, ABB, and other companies. Well, they were doing the same for the last 40 years, and nobody was asking them something different. And then some crazy guys came from MIT. They had a startup, and they had this crazy idea of using some new control ideas that were developed 20 years ago. And wow, now the robot can be by my side. And the others were, whoa, we need to do something. And 2 years later, ABB had Yumi, and KUKA had the other Iowa, robot, and new companies start to develop robots the same way. Okay, so companies tend to be less proactive if the market is very calm. If they got used to just those products, if someone new comes and show them that there are new opportunities, new things that can be done, they are going to move. Otherwise, they are trying to solve the production problem. They are producing and selling, producing, selling. And they need to solve these problems. Even companies from abroad, Brazil, international companies, if the situation of the market is very calm, they want to try to excite this. They keep things calm and just producing and selling.
Yeah, nice. I believe so as well. We can see it on the new space race that was maybe started by Elon Musk and all the small companies that was just crazy guys with money that will just invest in space. And then nowadays we are seeing that people are really looking forward to it.
Yeah, and it's the same when it comes to assembling aircrafts. You have the big ones. Now they are merging. Before we had the Boeing and Embraer, now they split again. I don't know what's going to happen, but Airbus merged with Bombardier. And where are the other companies? We are flying planes this very similar shape for decades. Nothing new is coming. And I was a child, I remember to see those, sci fiction books. Wow, this shape is different, like a wing and things like this, and we don't see it. So something new needs to appear to shake everything, and then people need to react.
Do we have any questions? Professor Todd, you want to comment and ask something? Please raise your hand if you want.
Hi, I have a question.
Okay, Bruno.
Professor Marcelo, thank you very much for your great talk. It was very informative for us as well. I have a question regarding innovation in agriculture. I mean, of course, you showed us a lot of innovative methods, but in my view, I don't know if I'm wrong. Please correct me if I'm wrong. But the main aim of the methods you showed us was to automate techniques that already are used in agricultural fields. So my question is, do you have an experience or experiences in which you or your team discovered other novel methods for agriculture as well? Thank you, Professor Marcelo.
Thank you, Bruno. As I told you before, it's a great pleasure to be here and to give this talk. Yeah, when it comes to have this big innovations, just big jumps, we depend a lot on instrumentation. So that's why we have this partnership with Option Photonics Institute in São Carlos, because we need these sensors to, in a smarter way, detect diseases, to detect weeds, or to, knowing that, understanding better the situation, and then we can do something to change. So we are very dependent on instrumentation. And this is an issue for us in Brazil, as I told you in the presentation, because we develop prototypes here at the university. We need companies. The ecosystem in Brazil is much better than it was 10 years ago. We have Embrapi. So if we have, even if it's a startup or a spin-off company that has some money to invest on developing new technologies, Embrapi can add some financial support, and then you can start something new. But for startups, Embrapi maybe is not the best option because they need money to start this. 1/3 of the road project, they need that money. And when it comes to instrumentation, everything is expensive. You need lasers, you need cameras, you need lens, you need to develop new instrumentation. So it's very costly. So in this area, in Brazil, we really depend on innovations on instrumentation. We need to, this can be something that the government could do for us, okay? Because agriculture in Brazil is different from agriculture in other countries. We have this tropical area, and the things that were made for Europe or Asia and the US, many times they don't work here. For instance, let me give you an example about the soil. We were working with Embrapa to understand better, to characterize the elements of the soil. But in Brazil, our soil has lots of iron, something that they don't have in Europe. So different components if you need to have all these soil samples to calibrate the system and to understand that what you're measuring here has a very strong relation with what would be measured in the lab, this correlation, okay? So again, instrumentation. So this is a problem for us to have more things that we can automatize in agriculture.
Thank you very much.
Professor Eduardo is also want to comment. Bruno, can you give him voice?
Okay, I can hear. I can. Julio, I'm sorry. Did you ask me to read the message of Professor Eduardo?
No. Just to give him voice on the audience. Professor Eduardo Todd.
I'm sorry. I think I didn't understand what you were asking me to do. I'm sorry.
Okay, just unmute him. Oh, because he's on.
All right.
He's on the attendees.
Oh, sorry. Just doing this right now.
So, Professor, you can.
Okay, thank you very much. First of all, thank you for your great presentation. It was a pleasure and it was very interesting to hear you. I am worried with a point. In Brazil, agriculture employs a lot of unqualified people. And it's great to increase the productivity and the production with automation, but I think that we have to prepare us for the consequences of that. Maybe at the same time, we should invest strongly in education of these people, or at least of the sons of these people, to avoid a big social problem. What do you think about that?
I agree with you 100%, Eduardo. This is the difference between have a planning, a long-term plan for the country and like a short-term plan. Usually our politicians have a short-term plan. They are just thinking about the next election. They should think more about our country, about the future that we want to give to our citizens. So I really agree with you. Today, agriculture is employing lots of people that doesn't have a good school level, if I can say like this. But things are changing. I can tell you the situation I saw some years ago in Recife. They were starting to have the Petrobras facility there. There was a harbor being built, and there were factories from suppliers for Fiat were going there too. And people in the region of Recife, they didn't have enough workers to harvest the sugarcane. They were like, I can't say like this, but they were importing, but they were hiring people from other states to go there and work with them. Okay, so what I can see is that the situation, the conditions to work in the farm are so hard that they prefer to work in factories, they prefer to work doing something else in the cities. So you need to find a balance between this. And for sure, the government must think about the future. They must give opportunities for these people that they are going to lose their jobs if we have more robots working on this area. But I see that they have time. They still have some time to do that, but they need to start acting now. Okay. Did I answer your question, Eduardo?
Yes, thank you. I think this point is very relevant because usually people believe that automation produces unemployment, but that's not true if you check the most developed countries like Germany, Japan, and others. But we have to invest in education in order to achieve good results. That's that.
Yes, this is the key word that our politicians should have in mind: education. This is the best way to develop our country, education.
Okay, thank you for your talk.
Thanks, Professor Todd. Professor Marcelo, we are not running out of time. At least we have 1 minute or two. And I would like to ask the question from YouTube because it's very nice. Maíra Saboya asked you, are there any efforts to adapt agricultural methods to make them more efficient for robots? What I always see is robotics trying to adapt to the environment and not the other way around. So maybe that's the point, because you are you are always mentioning the difficulties, the distance between the crops, and but maybe because it's made for humans, not for robots.
Yeah, I agree with her. There's a nice case that happened in the US with apple trees. So I have some colleagues in Carnegie Institute, the Robotics Lab, in a partnership with the American government. They could figure out a way to adapt the farm, the apple tree farm, for the robots. So it makes life much easier for them. But to do this, in Brazil, we need to have like a strong partnership with Embrapa, because Embrapa, you know, they give directions. Embrapa is one of the best research institutes that I know in Brazil. They really do a great job, and they can, working together with them, we can give some new directions for the farmers. And they will trust Embrapa. Everybody trusts Embrapa. I mean, so it's a way to change things, make my life easier, for sure, but increase the productivity and to have the trust of the farmers. I think this is the best way.
Okay, thank you, Professor Marcelo. It was a very nice talk, and a very nice talk with all the people that was watching. And thank you very much. You can, if you have anything to say to finalize, I'm just leaving the mic.
Yeah, it's just as I showed you in the presentation, we are open for collaborations. We like to share our toys, and I do believe in teamwork. So we are really open to work with you if someone wants to help us in this challenge. It's really challenging, but I do believe that this can change. The Brazil situation. This can really make us much better researchers and have a better way to feed our population and to grow the country. Okay, thank you indeed. It was really a pleasure. Thank you.
Thank you very much. Thank you very much for watching, everyone. Thank you, Professor, once more. Next, we have the next technical sessions of the LARS. Please watch the next. We are going to speak about aerial robots and many other direction of robots. Thank you, Professor, once again, and stay tuned.
Bye-bye.
So I believe Professor Douglas Macarat is the next chair. Professor Douglas, you can comment the session right now?
Yes. Okay, thank you. Hello, good morning, everyone. So this is the second session on aerial vehicles. We are going to have 3 papers being presented, and each one, they're going to have about 12 minutes for presentation, followed by 3 minutes of questions. Our first paper, it is entitled Onboard Instability Correction of a Flying Wing Unmanned Aerial Vehicle, and it's by Alisson Lucena and Luis Gonçalves. Alisson is going to do the presentation.
Bom dia, Professor Douglas. Gostaria de solicitar o vídeo, por favor.
Okay, also no problem. Emerson's going to play the video for us. Just a second. Hi, Emerson. The video doesn't have audio, so you have to mark that option to share the video audio.
I will present the work on body instability correction of a flying wing and manned air vehicle. This is a work by Alison Lucena under my supervision. When we are talking about UAV, these two types of UAV have some particularities. The planes, for example, they have less sustainability, so they need some velocity in order to be in the air. And this is a problem because it also has less payload. On the other hand, the flying wing, as it has a bigger area, it gets more sustainability. And with this, it gets more payload. So we can put, for example, a camera that was a request in a project that we were about to develop this kind of system for acquiring images. So besides these advantages, the wing has some problems, mainly due to the dynamic balance. In relation to the planes, for example, the planes have a warped wing. So once something as the wind or some maneuver has been done, it gets back faster to stability than the flying wing. Because the flying wing has a plane surface, it's more harder to stabilize it after this kind of event. So some choices have to be done since the beginning, and that's what we will talk about in here. The first thing, the variation of position of the center of pressure is responsible for bringing stability. Once we vary the position of the center of pressure, we are also varying the attack angle that it will fly. Here you can see that as more to the front, more we have the alpha, called the alpha angle, more to the front of the center of gravity. Okay, so we have chosen a flying wing with 1.20 meters. It has 0.22 meter in the extremities and about 35 centimeters in the center profile. Here we can see in the right as several other measures of our flying wing, and the control surface that makes this kind of UAV produces some desired movement are only the elevons. We have two actuators in here that control the elevons. Of course, they can be controlled in both in the same with the same angle. In this case, I will go down or up a little bit. And if I put one in one direction, the other in the other direction, the other sense, in this case, I can produce a roll to the left or to the right, depending on what you do, what is done with the elevons. Okay, since we have this control surface defined, we went to define the profile. To define the profile is a question of analyzing using a software. In this case, we have a software for analyze profile, and we took two profiles in order to be analyzed: the ZEG 12 and the SIPK 1.7/10. From these two, we got the lift coefficient, the drag coefficient, and also the aerodynamic efficiency, that is a division of both of them. And we also took the moment coefficient. To the end, we shows the drag, the different, we shows different profiles in the center and in the extremity. I'm going to talk about this a little bit later. Well, this is the illustration of the basic electronic that we have embedded in our system. We have a receiver type of the type Spectrum DX7 of 2.4 gigahertz with two receptors. As the battery chosen was a LiPo battery, turning 2.2 ampere. We also bought an autopilot, APM 2.8 for doing the autonomous flights. We have a GPS blocks and EO6M with, it has already a compass also. The servos used were at a Tower Pro 9 grams. And we also have a controller for this, for the powertrain, right? We have chosen a 3XL controller, the Rob King SS Series 2530. In the powertrain is a brushless motor and a Max CF2822, propeller APC 840. Okay, since we have this embedded electronics all chosen, we put a camera too. In this case, we show here a full 8D resolution. However, we have done another one that comes together with an autopilot based on autopilot that can substitute this previous one here. Okay, and the camera goes together. In this case here, we just put the camera for taking some pictures from there, with the resolution. So once we had those materials, we went to do the construction properly. This is the wing composed of polystyrene foam, and we have put some very thin fiberglass stringers in here in order to give more less instability to it. The profiles, as I said previously, in the center are different from the ones in the extremities, are different just in the twist angle. This twist angle guarantees that the stability in the extremity it is kept. If something happens, at least until it gets the stall, the stability in the extreme will be kept. even if losing stability in the center. This is a good choice. In general, people do that. Okay, our wing was covered with a self-adhesive vinyl cover, and then we put together all of the embedded electronic on it, and then Alison went to test it. In order to test it, we use the mission planning software. In this case, we are gonna do some autonomous flight in order to see if it works well, and the stability correction that we have put on board is the main contribution here. And we are going to see 3 modes of operation on it. The first one is without autopilot. This is controlled by hand using this radio. In the second mode of operation, it uses the stabilized autopilot, and we did a third one just with the autopilot without the stabilization. Here is the flight that we planned. It has 8 waypoints, and you can see the path that it has to follow, and after the last one, it should get back home. So at least from here, go to there and make like this pass. Here is an analysis of the pitch and roll movements with and without the stabilization. Here we can see that with stabilization, it is much better. Well, here is in the mode 1. Here is in the mode 2 stabilization, right? And here it gets again to mode 1 without stabilization. And here too, here is the roll and here is the pitch axis. Just to say, here is some images that we have captured from this wing. Another one. Here is the pass that was executed since it left from here, and here is the start of the autonomous flight. It almost loses itself in here, but then it went back to the point 2, point 3, point 4, 5, 6, 7, 8, and then it got back in here. It was supposed to come here. But that's okay. After it was here, we got again with the radio and returned to mode 1. So here, everywhere is mode 2 operation. Here is Alison. If you want to see him in a few minutes, that has built this wing for us. In order to get images, aerial images. So we have this wing now ready to do tasks necessary in monitoring. If we have a project that is about to be approved on this, and we are going to use it to get pictures on the sea, over the sea, no? To see if you have oil on the water and things like that. So thank you very much. I hope if you have questions, you can ask Alison, that he will be answering you. Thank you very much.
Okay, thank you for the presentation. Do you have any questions here or at YouTube? Let's wait just a few seconds. I have a question. Alison,
Ok.
all the control is made by the autopilot?
Me desculpa, eu vou só pedir para tu repetir em português, por favor.
todo o controle da asa é feito pelo ar do pilot?
Isso, tem uma sequência, né? É programada no controle remoto. Eu tenho ela totalmente controlada pelo piloto, ela controlada pelo piloto, estabilizada pelo ar do pilot, e também tenho ela totalmente autônoma. E também é feito uma configuração de segurança, onde ela vai atender sempre aos comandos do piloto, mesmo estando em um voo autônomo. Qualquer comando que passe pelo controle remoto, ela vai atender, é uma questão de segurança.
E o modo autônomo, ele também é estabilizado.
Isso, estabilizado, exatamente.
Any other questions? Okay, thank you for the presentation. We are going to go to the second paper of the session. It's entitled An Evolutionary Algorithm for Joint Trajectory Optimization in Aerial Challenge. And it's by Adson Alves, Murilo Ferreira, Esther Colombini, e Alexandre Simões.
Hello, you listen me?
Yes.
Okay. Can you see my screen?
Yes, it's fine.
Okay. Hello, I am Adson Alves, and I am part of the program, the graduate program in electrical engineering at São Paulo State University, USP, Sorocaba. Sorry. Okay. This presentation will process was follow: abstract, introduction, evolutionary algorithm, Petrobras Robotic Challenger, proposed approach, materials, methods, result, discussion, and conclusion. I will show my chart about an evolutionary algorithm for a quadcopter trajectory optimization in aerial challengers. Therefore, this work proposed an EA model developed to find the best travel trajectory for a quadcopter in the Petrobras Challenger. In the Challenger, a set of landing platforms that robot has to visit are displaced in the 3D space. To find the best trajectory possible, we optimize an EA over a low-level control that can take the quadcopter from point A to B. We vary our fitness function to support more complex decision. The soft-terrain loop technique was applied for a simulated quadcopter in the Coppelia simulated environment. The proposed approach was shown the capability to generate short trajectories while considering variables like UAV dynamics and energy consumption. A brief introduction: the UAV or drones have become extremely popular over the last decade. It's become commonplace to see small aircraft equipped with cameras and other sensors flying over the public place to capture journalistic images, produce professional videos, or even amateurs posting social networks. For the UAV carry out the delivery goods, for example, this vehicle must define its routes and check if its geographic position is correct. This problem has two particularities. The first involves an extra dimension, and the second, it is relevant when choosing the best route to consider the trajectories that will be executed by the UAV, which in turn depends on particularities of the vehicle, dynamic, energy consumption, etc. This work proposed a generic algorithm for UAV to define the best path for a quadcopter to visit all destination set points based on different optimization criteria. we can consider that evolutionary algorithm has 4 phases: the initialization, selection, genetic operation, and finalization. The Petrobras Robotic Challenger is within the RoboCup Brazil. In the simulated study and develop of autonomous and intelligent flying robots designed for inspection and operation in oil pipelines. The scenario comprised some platforms, and the UAV are expected to visit all platforms as quickly as was possible, showing robust flying controller and devices for handling and loading objects. And this is the website of competition. The proposal was to build the scenario in the simulation environment Copelli and test the EA for this. We divided into 3 experiments that will be explained below. Basically, the EA defines some routes and at random test the routes using a distance fitness, take the 4 best routes, and perform the crossover and mutation on the top of these results, thus generating new descendants called children. The process is repeated until the stop criteria is satisfied. Okay, the experiment 1. In this experiment, the fitness function was designed to consider the computed Euclidean distance between the platform sequence represented by each individual of the population. After completing the training process, the past sequence of platforms was sent to Quadcopter for execution and evaluation. This experiment represents the classical approach for the traveling salesman problem, which TA adapted to the aerial vehicle scenario. The algorithm focuses the shortest path without considering the quadcopter's dynamics. The experiment 2. The shortest idea path between platforms is not necessarily the same as the shortest trajectory for a particular quadcopter. This experiment incorporate elements such as the vehicle dynamic and the quadcopter controller into evolutionary approach. In this case, the fitness functions computed the integral of the quadcopter position, sampled by the simulator of time and the trajectories performed. The experiment 3. In third experiment, we investigate how the learning algorithm could consider other characteristics from the quadcopter. In this case, the fitness functions also consider the cost of UAV to execute the path in terms of its power consumption. This is equation used for this. And the result, the experiment 1, show us that according to the fitness function, after the 11th iteration, the algorithm reached its minimal, but it was unable to end the learning only after 100 iterations. Variables in maximum and the average values can be observed. This is the path in 3D space. Okay. Take a new test, but now in more challenging scenario, it is easy to notice behavior with many deviation, errors between the position and the actual base and performed by the drone. This behavior can be justified since in this experiment, the dynamic of aircraft were not taken into account. The Euclidean distance was the only parameter considered by the fitness function. the generated path does not consider the quality of the flight, was shown that the best path was expected to be reached if you had displaced about 24.6 units. For this example, the true trajectory executed by the quadcopter measured 25.5 units, 4% higher than expected. In a more hard scenario, this problem more drastically expected 42.1 units, executed 44.6 units, 5.90% a year. This is the result is experiment 2. Only near the sixth iteration, the algorithm reach a minimum value, like the other experiment variations in maximum value and the average can be seen in the graph. This is the path for this experiment. Since the evolutionary algorithm tested the candidate solution by measuring the actual distance traveled by the drone, the best performance achieved about 24.67 units overcome the actual traveled distance in the first experiment. This happens because the trajectory is selected considering the characteristic of the UAV flight. After execution, the best path, the drone traveled 24.80 units, only 0.5% higher than expected. The error rate was significantly lower than experiment 1, since the trajectory is the most suitable for this quadcopter. The difference in the values are due to the fact that the simulation is stochastic. Also, the learn and angular speed were significantly smaller than in its previous case. There is the fitness function of experiment 3. This is the path chosen by the algorithm. Since the fitness functions combine different metrics, distance and energy, the result is not numerically comparable to those in previous experiment. When executing simulator, the best routes was reaching 0.9056 units, approximately 0.2% less than expected value. Now, this is the linear frame and speed signal, and we can see that the first experiment, the signal is more disturbed, while the experiment 2, the signal is more harmonic. And the experiment 3, the strategy was apparently to avoid major efforts. Yeah. In conclusion, in this work, we propose to using evolutionary algorithm to optimize a path planning test for a drone in aerial challenger. We tested different optimizations policies. Experimental results show that optimization strategies that consider the drone dynamic and the end control were more successful in defining trajectories feasible for a drone. Were platforms that require more refined controller strategies to solve tasks with quality, both low-level and high-level controller have to be aligned. In this sense, the EA proposed to allow us to solve our tasks without requiring low-level fine-tuning, really optimizations, different research. This can be a great advantage when commercial robots are in place. Was future works, we want the testing of others multi-optimizations criteria, flight time, payloader, etc., and consider dynamic environments with replanning strategies. Yes, thank you for listening.
Okay, thank you for presentation. Do we have any questions here or at YouTube? I have a question, Ricardo. Addison, sorry.
No.
On experiment 3, are you considering the energy and the distance, just like in experiment 1, or are you considering the distance as in experiment 2?
In experiment 1, I consider only the Euclidean distance, similar to the Selous-Mann problem. And the experiment 2, I consider the dynamic of UAV in fitness functions. When I talk the dynamic, I talking about to define my distance to platform A to B. I look the real distance executed by the simulation, and the experiment 3, I input in my fitness functions the energy consumption that I follow this equation that I present in last slides.
Do you have any other questions here? On experiment 2, are you considering that the vehicle is moving at a constant speed?
Yes. No, it's the real movement, yeah, because I put my drone I executed the simulation, and the depends of the platforms that he select, the velocity alter, because I put the fly to follow 100 interactions until independently the distance of platforms in 100 interactions, the drone achieve this platform.
Okay.
The velocities don't is constant.
Okay. Okay, thank you for your presentation. We are gonna go next to our last paper of the session. It's entitled Deep Reinforcement Learning for Mapless Navigation of Unmanned Aerial Vehicles. It's by Ricardo Grando, Júnior Jesus, e Paulo Deus Jr. Okay.
I would like to ask to pass the video. Hello there. My name is Ricardo Grando, and I'm going to present the work Deep Reinforcement Learning for Mapless Navigation of Unmanned Aerial Vehicles. Navigation-related tasks for UAVs are commonly done with image-based sensing approaches, like SLAM, for example. However, these algorithms may demand high processing power hardware, which can be heavy and difficult to embed into UAVs, mainly if this UAV is a small one. It may also demand manual procedures to achieve a good performance. At the same time, recent works with terrestrial mobile robots have achieved good performance with deep reinforcement learning for autonomous navigation. The so-called mapless navigation have less dependency on accurate sensing data, being much more reliable in this case. In this context, the agent learning is the map itself. In this work, we focus on demonstrating how effective deep reinforcement learning can be when applied to mapless navigation of UAVs. We set up 2 tasks in 2 different scenarios and compared our approaches with a traditional algorithm that can be used for mapless navigation. We based our approaches in 2 state-of-the-art algorithms for deep reinforcement learning, which are the deep deterministic policy gradient, the DPG, and the soft actor critic, the SAC. The methodology. First, we described a real UAV in simulation with its physical properties. We described it in the gazebo simulator. So figure in the left shows our real vehicle, and the figure in the right shows our described vehicle already deployed in the gazebo simulator. Then we developed two scenarios to train and test our approaches. The first one is a single cube of 5 meters of height, while the second one is like the first one, but with 4 obstacles added to it. These obstacles, the idea of these obstacles is that they simulate drilling hazards. For example, drilling hazards are commonly found in oil platform ships, and the inspection of these obstacles can be done by UAVs, for example. We used 20 samples of sensors readings, the last action and the relative information of the target, which are the distance and the relative angle for the state of our agents. So we have 20 samples of sensor distance readings, the previous actions, the action, and the two information relative to the target. The action itself, we set up in a way that it provides the linear velocity and the variation of the delta yaw, the variation of the vehicle yaw angle. The laser samples is from a simulated LiDAR with 270 degrees of ranges, equally spaced in 13.5 degrees. But like I said, the action, it provides the linear velocity and the variation of the robot's yaw. We set up the robot's X and Y velocities in the gazebo simulator by converting these actions, which are in polar coordinates, to the Cartesian coordinates of the gazebo simulator. The network of both agents has 24 inputs. The laser samples, the 20 laser samples, the previous linear velocity and the previously delta yaw, as well as the target distance and the target angle, while the output provides the linear velocity and the variation of the yaw angle. Also, the methodology for the DPG-based approach, we set in a way that it has 3 reading layers for the actor network with 500 neurons each layer activated with the ReLU function. For the linear velocity, the neuron in the output, which provides linear velocity, we use the sigmoid function with limits ranging from 0 to 0.25 meters per second. For the delta yaw, the neuron that provides delta yaw, we use the tanh function with ranging from minus 0.25 radians up to 0.25 radians as limits. The critical network, we used also 3 reading layers with 500 neurons and the ReLU activation. For the SEC-based approach, SEC-based approach is like very similar to the DPG-based approach. The main difference is that we used tanh activation, the tanh function, as the activation function in both neurons, in both outputs, but we used with the very same limits. We used the ADAM optimizer with learning age of 10 raised to -3 for both networks in both approaches. We also used a replay memory of 50,000 samples of a buffer and a mini match of 256 samples. We also defined a rewarding and penalty system, which is quite simple. A positive reward of 100 is given if the robot achieves a goal within a distance of 0.25 meters. A negative reward of -10 is given if the robot collides with some obstacle or with the wall. We also give a small reward if the distance to the target in this step is lower than the distance in the last step. So we encourage the agent to learn to go towards the goal. We set a limit of 500 steps per episode and trained with aleatory generated targets. We trained the agents for 1,000 episodes in the first scenario and 5,000 episodes in the second scenario. The results did two tasks to evaluate our approach. The first one, the agent should navigate from a starting point to a specific target. So as you can see in the figures below, both agents managed to achieve the target, as well as did the traditional algorithm that we use to compare, the Lee controller, a geometric tracking controller. This algorithm also managed to perform this test. So in the figure in the left shows the SEC-based method, figure in the middle shows the DPG-based method, and figure in the right, the traditional algorithm. As you can see, both the deep reinforcement learning methods and the traditional algorithm managed to perform this test. In the second environment, we also set a target, but with an obstacle along the way. So the obstacle needs to be bypassed to avoid a collision. In this task, as you can see, while our approach managed to bypass and successfully achieve the target, the traditional algorithm collided with the target along the way. Again, a figure in the left shows the SEC-based method, in the middle, the DPG based method, and in the right, the traditional algorithm. As you can see, both deep reinforcement learning managed to bypass the obstacle and reach the goal, while the traditional algorithm failed. We also set up a second task. In this task, the robot should follow a path of multiple targets. It's basically a path following task. In this scenario, in the first scenario, both agents and the Lee controller managed to perform an accurate path and perform the task. As you can see in the figures, the traditional algorithm was slightly better, as you can see, but both the deep reinforcement learning approaches managed to perform this task as well. However, like for the first test, in the second scenario, while our approach managed to perform a path without colliding with any obstacle in the environment, the traditional controller failed once again and collided with an obstacle. As you can see, both deep reinforcement learning methods managed to bypass the obstacles and go to the final position. So the conclusion and future works. So the proposed deep reinforcement learning approaches are able to perform a goal-oriented mapless navigation by only using the robot's localization data and some samples of a laser ranging, some samples of a LiDAR. The results obtained in both environments that we trained show that the robot is able to learn to bypass obstacles and reach a desired goal. However, when controlled by a classic geometric tracking controller, as we did, the UAV indeed performed very well in the first environment for both tasks, where there are no obstacles, but failed in the second environment where there are obstacles. So as future works, we aim to make the 3D navigation as well, and use it, test it to implement it in our real robot, in our real UAV. So thank you all for the attention.
Okay, thank you for the presentation. Do we have any questions here or at YouTube? I have a question. Why have you chosen to compare it with a simple controller instead of another, for example, reactive approach such as potential fields?
Yes, we compared with this the controller, this geometric tracking controller, because it is already implemented in the rotor simulators, the rotors framework. That is the framework that we use to describe our vehicle. So it was an easy way to find a algorithm to compare our approaches.
And considering the 3D navigation you mentioned as future work, what would you have to change on the current methodology?
Yes, we have already done the 3D navigation successfully in simulation. Basically, the basic difference that we did is we created another action, which is the altitude velocity, which makes the vehicle able to navigate in the z-axis. That's basically it. We also had to add another angle, which is an angle with the z distance plane to make this the 3D navigation work well.
So you're just considering that your vehicle can move like up, down, and forward and side. It can move. It cannot move on the diagonal.
No, it can move in the diagonal because the actions we can have any value for the actions in for any.
In a continuous space.
Yes, it's a continuous space. Okay. So you don't need to go to, for example, go right and down. You can go in the diagonal up, down.
Actuate at the same moment. All right. Do you have any questions here? Okay. So thank you for the presentation. And this concludes our session on aerial vehicles. Thank you all for being here.
Hi, so the next session will be chaired by Milena Faria. I believe Milena is here. Milena, are you ready?
You're ready.
Now, okay.
Okay. Good morning, everybody. Now we start the third session of aero vehicles. We have 3 papers in the section. Just to remember, each paper has 12 minutes to be presented and 3 minutes for question. Besides, authors can present by themselves or use video. The first paper of the session is entitled Performance Indices-Based Tuning for Barometer-Aided Industrial Navigation Systems. The presenter is Leonardo Alves. Leonardo, do you prefer present or use video?
Good morning. Could you please play the video?
Yes. So go on.
Hello everyone. My name is Leonardo Alves, and I'm here to present to you our article entitled Performance Indices-Based Tuning for Barometer-Aided Inertial Navigation System. This article was also written by Rogério Filho and Lucas Paiva. Our advisor is Felipe Oliveira Silva. This work was developed at Federal University of LARS. Introduction. Navigation system is used in many different applications. Can be used in terrestrial, marine, aerial, and space applications. The main purpose of navigation system is providing information of position and orientation during a process of locomotion. Inertial navigation system, or INS, is a kind of navigation system. Since we have the initial condition, INS is a standalone navigation system which numerically integrates accelerometer and gyroscope measurements. A pure INS has a drawback that the vertical channel is unstable. To solve this problem, a fusion of barometer with inertial sensor are used. In this fusion, it's necessary to calculate some gains to guarantee the stable, fast, and reliable response. One method to calculate these gains is using performance indices that we are going to study in this article. Strategies for INS vertical channel stabilization. In this figure, we represent a simplified diagram of INS vertical channel, where AD is the inertial sensors measurements, HD is the output altitude, 2G over RE is the gravity contribution. As we can see in this figure, the main reason of the instability of vertical channel is the positive feedback. To solve this problem, three different mechanizations are going to study. The first one is the second order vertical channel mechanization using 2 gains, C1, and C2. This mechanization was studied by Seores and Tittle. And below we have the transfer function for this mechanization, where HB is the barometer measurement. The second mechanization is the third order vertical chain mechanization using three gains, C1, C2, and C3. This mechanization is studied by Becker, Rogers, and Savage. And below we have the transfer function for this mechanization. And the last one is the third order vertical chain mechanization using four gains, C1, C2, C3, and C4. This mechanization is studied by Seores. And below we have the transfer function for this mechanization. Performance ends. In this article, we're going to study four criterions of performance ends. The first one is the integral of absolute error. The second one is integral squared error. Third one, integral of time multiply absolute error. And the last one is the integral of time multiply squared error. Each criterion has a different cost function as shown in these equations. Results and discussion. This simulation was divided in two steps. The first step, we're going to analyze the mechanization for each author and to see which one, which tuning has stable response and reliable response. After that, we are going to pick the best one, and the second step, we are going to compare with the tuning gains that we are going to calculate using the performance ends. On the left, we have the table with traditional empirical tuning gains. That's the gains that each author used in each mechanization. On the right, we have the roof mean square error in altitude and vertical velocity. As we can see in this table, Seores order 2 and Becker order 3, they have the highest values of errors. And this can be explained looking at those two figures. On the left, we have the altitude error. Seores order 2 and Becker order 3, their errors are increasing during all the time. That explains why they have the highest values of errors in altitude. Savage order 3 has error more stable from the others authors. Looking at the figure on the right, vertical velocity error, we can see again Seores order 2 and Becker order 3, their errors are increased during all the time. And Becker, in the first 20 seconds, a Savage order 3 has the highest values of error, but after that, his error start decreasing and oscillating over zero. On the left, we have the step response for each tuning. On the right, we have the summarize of this unit step response. We're going to analyze into three aspects: rising time, settling time, and overshoot. As we can see, Savage has the faster rising time and faster settling time, and Seores order 2 has the lower overshoot. Summarizing the error in altitude and error in vertical velocity and the step response, we can affirm that Savage is the best one because his error is stable and it is faster than the others authors. Because of this, for this reason, we are going to pick Savage 1 to compare with the tuning that we're going to calculate using performance ends. The performance ends we're going to divide into two simulations. And for each one, we're going to calculate for each criterion the set of gains. More than 2 million of gains were calculated and to calculate. On the left, we have the performance tuning gains and the gains that we are finding for each simulation. On the right, we have the roof mean square error in altitude and vertical velocity. As you can see, the error in altitude and error in velocity, the difference between the salvage and the tunings that we calculate is very small. And we can confirm looking at those two figures. On the left, the altitude error, and the right, vertical velocity error. It's almost impossible to distinguish the values from salvages and the tunings that we calculate, because the values is almost the same. Now we have the step response. The step response, we can see the difference between them. On the right, we have the unit step response summarized in the table. As you can see, all those tuning gains that we calculate using performance index, they are faster and lower overshoot. As you can see, GISE1, he has 3 seconds of rising time, 24 seconds of settling time, and only 12.33% of overshoot. Conclusions. In this article, we study mechanizations consolidated in the literature, and we analyze 6 different mechanizations, 2 of Ciolis, Tittle, Becker, Rogers, and Savage, and we simulate them and to pick the best one. Also, we studied performance indices IAE, IEEE, ITAE, ITSE, and for each criterion, we calculate the set of gains, and also we simulate searching the best set of gains. And also simulate, we see that GISE1 is faster and has lower error in vertical and vertical velocity than Savage. However, error in altitude was higher than Savage. For future works, we propose to study optimal and robust control and extend common filter. And these are the reference that we are using this article. Thank you.
Thank you for the presentation. Congratulations to your work. Do we have questions on YouTube or here? No, so Leonardo, I have questions.
Okay.
I was wondering if you deal with noise caused by wind.
Sorry, repeat, please.
How do you deal with noise caused by wind, or you didn't try to deal with this problem in your work?
No, we simulate initially, and and we in these errors we put the noise wind also.
Ah, okay. And okay, just for curiosity, you put in the future works that you are going to test extended common filter and also optimal or robust control. But did you already try to test this kind of strategies to as a turning mechanism?
Not yet. We are studying to improve. We study to provide in the next step.
Okay. So thank you very much. Congratulations to your work. I particularly found it very interesting. Congratulations once again.
Okay, thanks.
So we can move to the second paper. The paper is from the student Thiago Santa Maria. The paper is entitled Path Following Problem Solved by NMPC Controller Applied to a UAV. Tiago, do you prefer present by yourself or by using video?
I will present.
Okay. So, good luck.
Hello, everyone. My name is Tiago. I will present the paper Path Following Problem solved by an NMPC controller applied to a UAV. I'm from Federal University of Juiz de Fora, and let's do it. And a brief introduction. NMPC applications on path following are common, and the paper 2, they use NMPC as a problem, as optimization problem. NMPC is generally optimization problem. And the papers 1 and 3, they use NMPC for path following, but on a ground mobile robot. And all information used was from a camera in these papers. And then on the actual paper, we will use the same algorithm, but with only camera 2, but to an UAV, not to a ground mobile robot. And we also address track and follow the path line and environments containing high illumination issues and flaws on the line, like the next slide will show. Cases of like this, high illuminations can be a problem, and small resolution, like in this in left side. Like we can see, it's hard to identify this portion of the line above, and a controlled and laboratorial line, like in the paper 1, where they try to solve the same problem on a ground mobile robot. And we will address these kinds of image serving problems too. My main objectives of this paper focuses on utilizing standalone NMPC controller and NMPC combined with an PID, which functionalities to smooth control actions and oscillations, just to help the NMPC. We use both techniques together. And this paper also will others, like stated before, failures and flaws in the segment caused by light, illumination, time, whatever. And we will use a calculable virtual trajectory to help the path following failures. We also propose a variable linear velocity profile based on track converter, allowing the UAV to complete the tasking and less time without reduce the errors. And the problem formulation, like we can see, stated here on the left side, superior view from UAV onward frame and with robot frame, and the side view. And the stated this Z variable is this longitudinal error. The phi is a yaw tax error from the UAV. Everything here is utilizing the camera, like we can see here. And the point PF is the standard 0, the center of the camera, which we will be utilizing for all these accounts. We will do utilizing the normal vector and the tangent vector, like stated here in this image. For the problem formulation, x, y dot, and phi dot, utilizing this equation for, like we can see, CS cosine and sin, just for space problem here. That's not a problem. And for linear velocity, we state these 3 here, u, v, and k, which is related to x, x, y, and k is a pitch rate from the UAV. R is the main control action we utilize here, the yaw angle rate. This will be used for control the UAV. We applied that equation 1 to a reference system as SF, and they are related to tangent vector and normal vector, stated before. And we will get z dot like equation 2 and S dot equation 3 here. And Z is the wavy side error, like stated before, and phi r, it's important, angular error for the UAV, stated related to the center of the camera, the point PF. We use them to the trajectory curvature C, and it's calculated by equation 4, like you can see here. And we use the point PF, the center of the camera, standard 0, and 2 neighbor points to calculate the curvature, estimated curvature from the image, obtained image. Equation 5 can be obtained in the literature, it's easy. And we find this equation here. And mixing them, we find the equation 6, x e dot and z dot, we stated before, equation 3, and the equation 5 here. And we call phi r dot as an UOPT. What is this? UOPT is the optimal value from the optimization problem and the NMPC controller. And the XE is the state error vector. Rearranging the equations, we found this equation 7 here, the main controller. We use this equation. We need R, the variable for equation service control action, which we will send in each interaction. The methodology utilized here. 3 control approaches will be evaluated in this paper: the NMPC plus PID and the NMPC standalone, and we use a classical PID alone too. The problem in this case consists of a particular case of optimization control problem, like stated before. The NMPC works on an optimization problem, and per the solution utilizes the Keynote toolkit, which as an open source optimization problem solver. It's very easy to use. The linear velocity proposed in this paper, like says before, we utilize U and V, like X and Y axis, and the pitch rate key. In this paper, we choose constant velocities 0.4 and 0.7, and the variable velocity profile, which is we utilize the curvature to estimate the better velocity for that place. This is the NMPC control proposed in this paper, and we will minimize this equation 8, which key and R are the positively defined matrices for weight deviations. And the most important here is the TP, predict horizon, which needs to be better than the control horizon, needs to be small than the predict horizon here. And everything is subject to these constraints. And this is the optimization problem from this paper. And the control scheme proposed the NMPC plus PID utilizes sensors only from the UAV and information from camera to localization, Z, H, and phi r. The NMPC here, this block has the optimization together, UOPT. It will send the R variable back to another evaluation and to the PID, which will smooth control actions and get it back to the UAV. For the track failures treatment, we utilize window masks, which called in that form, where in this case, the line can be clearly defined, where the black is not the line and the white is the line found for the work. And like we can see, the standards here will be in the center of the camera, like here. In this case, they will calculate 2 adjacent points and calculate the curvature for movements of the NMPC. We also introduce these windows utilizing the above part of the image and the lower part of the image. Like we can see here, utilizing the standard 0, which can be found in this one. But in this case, on the controlled place like this, the standard 0 can't be found here in the center. And we utilize the portions of above and below. And like we can see, we utilize points to calculate a virtual trajectory to overcome the problem on the standard 0 not be found. And the fixed windowing, which we utilize first, utilize equally separately 3 parts. The problem here is on the side where we can see it can be a problem. A point will not be calculated here because it's a small amount of the image here, and we applied our flexible windowing, which always we will calculate a point on small portions here, and it will overcome this problem of calculation. For the results, the variable windowing, like stated before, it gets small variations on the same error, like 0.6, and the fixed got 2 or almost 1. It's big errors. And the control comparison, we utilize the mean squared error and EAE. A mean squared error here, like we can see, the NMPC plus PID has lower errors compared to the others. And for the linear velocity, like we can see, constant linear velocity has more time to complete the task. And the variable linear velocity do not lose so much errors. The errors are low, and we can still perform the tasks on a good time. Here the results for the EAE. Like we can see, the NMPC plus PID has good results, reliable results compared to the others. In all of these variables here of the study, control effort and all longitudinal errors. But it falls on TV indicator, and the lower is TV index is better for the noising and other problems. And MCPID has high amount of TV index. You need to overcome this problem in the future. And it's the control comparison stage. I will say thanks for everyone for watching this. And for future works, we intend to utilize this paper and overcome these problems stated before, like TV index, and utilizing this on a real place where we utilize only simulations. That's what we have for the future. Thanks, everyone. These are the reference utilized in this paper.
Congratulations, and you presented very well. So we have questions here or on YouTube. Okay, no questions. So I have. It's a really nice challenge that you are facing, and you propose a solution for it. So very nice. The first question that I have is why you use NMPC for path follow? Did you try another controller besides PID?
No, this will be a next step to utilizing another controllers to compare here. The PID was used because it's easy to implement and easy to compare with an NMPC. We have this another papers from ground mobile robots from that we stated here. And they used an NMPC for that problem. We think that it would be cool to put that on a UAV to see if it works well, like in ground mobile robot, and compare that to.
Yeah, it's really nice. You took a work from a terrestrial vehicle and put it on a aerial one. So congratulations. So I was really curious about why NMPC. The other question is, your results only rely on simulation, or you have some results in a real prototype?
Well, like I stated, it's from simulation. These results from the paper is from simulation. We were working on real environment. We had a few problems because of war problems. But we were working. We did a few tests from Windows Max on real image, like I stated on the start of the paper. Utilizing that real images, we used and see that works well. We didn't put it in the paper because we didn't make sufficient works and tests to put that into the paper. But
Yes,
we're proceeding on that.
I was wondering because you have really differences from real and from simulations, and you're using images. So this is what my question. And finally, I promise, which kind of civil image information was used for the windowing masks?
HSV cone. We utilize the HSV cone to make a state which is the line, which is not the line. And the windowing masks will be utilized for the portion found in the pixels image. Like I state, eu não sei falar em inglês isso,
No problem. Take your time.
A imagem é 800 por 600, ela é separada em 3 partes iguais e basicamente no jornaleamento flexível, Window Flexible Masks, nós utilizamos a quantia encontrada, porque a linha ela pode não ser encontrada dentro desses janelamentos. Então, se for encontrado um pouco no janelamento de baixo, nós não vai utilizar 200, vai utilizar 100 e calcula, mas um ponto vai ser calculado lá de todo jeito. Desculpa, sorry.
No problem, no problem. Okay, thank you very much. So now we move to the final paper of the section, from the session. The paper is entitled Visual-Based Autonomous Unmanned Aerial Vehicle for Inspection in Indoor Environments. The presenter is Ricardo Bendin. Ricardo, do you prefer video or present by yourself?
I would like to ask for the video again.
Okay, thank you.
Hello there, my name is Ricardo Grando, and I'm going to present the work Visual-Based Autonomous Manned Aerial Vehicle for Inspection in Indoor Environments. The use of UAVs has become popular in industry, research, and military. Recent advances in 3D printing, sensing, embedding processing, and battery efficiency allowed a broader development of smaller and more efficient aerial vehicles. Nowadays, most UAVs are designed to operate in outdoor environments, being fitted and dependent on accurate GPS data feedback. They ended up being often manually employed by some kind of external operator. In this case, a failure of communication with the vehicle to send or receive commands can result in loss of data, inaccurate navigation on, and even possible crashes. In this work, we propose a visual-based UAV with embedded online intelligence capable to maintain stable flight, navigate, and locate itself in indoor environments. With our approach, there is no need for any external operator or any kind of onboard processing. We evaluate our vehicle in a real indoor environment that simulates an oil platform environment. So figure in the upper right shows the vehicle in the modeling and design phase, and the figure in the down right shows the vehicle already deployed in the test environment where we conducted the evaluation of our vehicle. The hardware setup, our vehicle was designed to have all processing embedded in it. The idea is to avoid any kind of use of external processing. We used a quadcopter-based frame of 45 centimeters of diagonal. We use propellers of 10 inches in motors of 1000 kVs. We used a Pixelcon flight controller as our main flight controller. We used the ZEDGE stereo camera to perform the visual inertial odometry. So with this camera, we get the visual pulse, which we use as the main pulse in our vehicle. We also used a monocular camera to perform the detection. We put this camera pointed to the ground, so we could make all the detection of things in the ground. We also used the Jetson Nano as our onboard computer. So with this computer, we did all the processing embedded in our vehicle. The software setup. The first step of our software was to change the Autopilot source code. The Autopilot is a framework for aerial vehicles. We compiled a firmware version of Autopilot that uses pose instead of visual pose instead of the GPS. By default, the Quadcopter, that is the Autopilot session of aerial vehicles, has the GPS feedback as the main information to define the pose. So we change it to have the visual pose that we get from the Z camera. We get the visual pose, as I said, from the Z camera and send this information to the pixel cone using the Mavericks interface. So the pixel cone gets this information and defines the position. Then we developed a ROS-based mission planner to send and receive commands to get the state of our vehicle. We then use this ROS-based mission planner to create tasks to test our robot. So figure in the right shows the electric graph of our system with the Z camera, with the node of the Z camera, the Mavericks nodes, and the communication between them. We also use the gazebo simulator and all other resources available to simulate our vehicle. The idea is that we could evaluate our codes before deploying the codes to the vehicle. So we could have, the idea is to have better results. So figure in the right shows our vehicle in the simulated environment of the gazebo simulator. The testing environment, we tested our vehicle in an arena that simulates common tasks for UAVs of an oil platform. These tasks can be inspection, navigation, for example. This environment provides many challenges, like having to locate, navigate, read information from the scenario, among others. This test environment that we used, we also described it in simulation as well to test our vehicle. So figure upper right shows the real scenario, the real testing scenario, and the figure down right shows the simulated environment in the gazebo simulator. We conducted 2 tests to evaluate our vehicle. The first test we called the navigation test. The idea is in this test is that the vehicle should autonomously go from a starting base in land at a ranging base. This environment that we used was the 2019 Brazil Open Flying Robot League, the scenario of this competition. So the GIF below in the left shows the scenario, our vehicle in the scenario, the real scenario, performing this task. So the vehicle should go from a start base in the ground and go to a ranging base. The figure in the down below, down right, shows the simulation in the gazebo simulator of this test. The idea is, like I said, is to analyze the vehicle visual-based location and navigation capabilities, as well as the ability to correctly detect a base and adjust itself to perform the landing. As you can see in the GIFs, our vehicle managed to perform this task in both scenarios. We did this second test. In this test, the vehicle should detect the information displayed by a simulated gas sensor placed in a ranging base again. So the vehicle should go over the hanging base and read the sensor numeric information using its camera pointed to the ground. The idea is that the vehicle should maintain a very stable flight and accurate navigation to be able to read the information and show the correct information. So figure in the left, down left, shows the test in the real environment, the competition scenario, and in the figure down right shows in the simulation scenario as well. So the conclusion and future works. In this work, we presented an autonomous visual-based UAV with embedded online intelligence capable of performing tasks in indoor environments. We tested in an indoor environment that simulates an oil platform scenario and described as well on the gazebo simulator to facilitate the development of our software system. All the software system that we developed was based on open source frameworks like Autopilot, for example, or even Mavros. Our strategy that we developed, the vehicle that we developed, the system that we developed was employed to win the 2019 Brazil Open Flying Robot League, or the Desafio de Robótica Petrobras, in the 2019 Latin American Robotics competition. We won this competition among other 11 teams all over the nation. So as future works, we aim to improve the robot's embedded system, to increase the overall processing capability and the vehicle autonomy. So thank you for the attention.
Thank you, Ricardo. Congratulations. Your work is very interesting. I really like it. So we have questions on YouTube or here? Okay, no questions. So as you have a good work, I have questions. This is the law. First one is that you stated that you tested your vehicle simulating common tests that you perform, that a UAV could perform in an oil platform. Yes. But an oil platform is an outdoor environment. Did you consider disturbances in scenarios such as wind, or even the fact that the platform has some movements due to the water?
In the real scenario, real simulated scenario, the platform, we didn't, because it was in our environment, in a closed environment. So we didn't. I don't believe we had many wind, maybe a few. But in simulation, we used the simulation of wind using we use some simulation of wind, but not much strong simulation.
Yeah, because this is a real problem in oil platforms. So wind and the movement of the platform due to the water. So maybe you could also consider it as a future work.
Yes.
Another thing that you say is that your vehicle should maintain a very stable flight. So when detecting these markers, did you apply some control strategy?
Yes, we have to go to the very close to the marker to be able to read the information that has in the marker. So we had to centralize the vehicle very slowly to be able to read the information and to send some external signal.
So which control strategy?
It's basically we verify the position.
Just to verify the position of the marker, and when verified, you go slow and take off.
Yes, if for example, if the position is on the left, we adjust the vehicle to go.
Okay.
In that direction. Simple as that. Very simple.
Okay, this is my questions. Thank you very much for your work and for your presentation. I think we conclude the third session of Aero Vehicles. Thank you, everybody.
Thank you.
Thank you very much, Milena, for coordinating the session for us. We'll be back after lunch, after the break for lunch, with the two last technical sessions of LARS SBR 2020. It's going to be two sessions on vision sensing, mapping, planning. And then we'll have the contest on thesis and dissertations on robotics for the master dissertations and PhD thesis. And then we conclude LARS and SBR 2020. I'll see you all after lunch.